I'm now going to introduce you to probabilistic context-free grammars, describe a couple of fundamental quantities that are relevant when using probabilistic context-free grammars to model sentence-level understanding, and describe the fundamental algorithm for incremental left-to-right parsing with probabilistic context-free grammars. So a probabilistic context-free grammar, or PCFG, is very much like a context-free grammar. Like a context-free grammar, it has a finite set of non-terminal symbols, a finite set of terminal symbols, a start symbol within the set of non-terminal symbols, and a set of rules, each of which consists of a single symbol from the non-terminal set followed by some sequence of symbols from the non-terminals and or terminals. What's new in probabilistic context-free grammars is a mapping from the rules of the grammar into probabilities. And so every rule will be assigned some probability, which will be a non-negative real number. And in the most basic definition of probabilistic context-free grammars, the property holds that the sum of all the probabilities of all the rules that begin with the same left-hand side symbol is 1. So you can think of this as a conditional probability distribution, in some sense, of the probability of the right-hand side alpha given the left-hand side x. This is actually a kind of stochastic branching process. And PCFG derivations and derivation trees are just like for context-free grammars. The probability of a derivation tree is the product of the probabilities of all the rules that had to be applied in order to derive the tree. So here's an example. This is actually the simple PCFG, the simple context-free grammar that we looked at earlier on. I've just attached probabilities to it. So all the probabilities of rules that have a unique a left-hand side, that is, that rules whose left-hand side appears only in one rule, is probability 1. So since the only thing that S can do is rewrite as NP and VP, its probability of that rule is 1, and so forth. But there are two rules, the NP rewrite rules and the N rewrite rules, that have two different possibilities. In these cases, we have probabilities that are less than 1, but the jointly sum to 1. And what I've illustrated in this tree here is that all the parts of the tree for which the rule probabilities were not 1 are annotated with their rule probabilities. So for example, the probability in this grammar that NP rewrites as NPPP is 0.2, so this little part of the tree gets a 0.2 around it, and so forth. And then to get the probability of this tree, I just multiply through all the rule probabilities as you see at the bottom. And what we find is that the joint probability of this tree, including all of the words, is 0.032, which is sort of a small probability in some sense, but it's actually an extraordinarily large probability to put on any one tree for one string in an infinite language like this. So that's a simple example of the application of a probabilistic context-free grammar. Now, we learned just now how to calculate the probability of a tree. It's also useful to talk about the probability of a string. That is, how probable does a grammar make a string in the language? And that probability is just the sum of the probabilities of all the trees whose yield, that is the left to right sequence read off of the leaves, of the terminals that are generated, is identical to the string. Another very useful quantity for studying incremental processing is the probability of a string prefix, the probability that the beginning of a string will be words 1 through I. The probability of that is going to be the sum of the probabilities of all the trees whose yield begins with W1 through I. So it's just the sum of the probabilities of all the strings that are consistent with the prefix, and since each string is the probabilities sum of the trees, you get the probability of all the trees that are consistent with the prefix. Given string prefix probabilities, you can now do things like compute the conditional probability of a word given the preceding words in the context. P of W sub I given W1 through I minus 1, for example, in a model where we're only conditioning on preceding words in the same sentence. In order to get this, we just take the ratio of the probability of words 1 through I and the probability of words 1 through I minus 1. That's the definition of conditional probability, and that gives us the conditional probability of the next word given the context for the grammar. Now, interestingly, you very, very quickly run into problems of inference over infinite tree sets. And it's useful to think about this for a moment, because it turns out that there are good ways to manage this inferentially, which might shed light into sort of some of the kind of machinery that might be going on in minds and certainly would needs to be implemented for artificial agents. So this is an even simpler version of the previous grammar. Here, I'm just taking the root category as noun phrase, all of the same rules and terminal symbols and terminal rewrites apply here. I've set the probabilities to be such that the probability of noun phrase go to determiner noun to be 2/3, and probability of noun goes to dog is 2/3, and then the remaining 1/3 probabilities for the other rewrites of those categories. And let's start with a very simple question, which is, suppose that your sentence starts with the word the. What is the probability that the next word is dog? Now, if this is not immediately obvious to you, and it's not necessarily that it should be, take a moment, you can pause here and think about it until you come up with your answer. What do you think that probability should be? The conditional probability of dog given start of sentence the. Ready? Okay, intuitively the answer should be 2/3. And the reason for this is very straightforward. Given that the first word of the sentence is the only thing that's possible in this grammar is that the next word has to be either dog or cat. Because, well, we started with NP and we may have invoked this rule from the root of the tree one or more times. So we might have actually done something like NP goes to NP-PP and so forth. But eventually, in order for us to get a word, we have to, at the end of the day, invoke a rule of the form NP goes to determiner noun. And then the first word was noun, was the. And then this has to be something. And the only words that N can rewrite are dogs and cat, dog and cat. And so we're really just boiled down to the probability of dog or cat given a noun rewrite. And you can just read those off of these rule probabilities up here. So that's the intuitive answer. How do we get to that intuitive answer in a generalizable way that preserves the computational principles of probabilistic inference and can deal with arbitrary grammars? So this was a special case where we were able to reason about it explicitly and it was sort of obvious what the answer is. But how do we implement this so it happens automatically? And there are some challenges that arise, which are as follows. So based on the definition of string prefix probabilities, we should be just enumerating the trees that cover the string prefix, the dog, and divide by the probability of those trees summed, divide that by the total probability of the string prefix the. But there are infinitely many trees, so you would be stuck with an infinite sum. So the infinite sum involves an infinite series of this form, right? So we could have, it depends on how many times we've invoked the noun phrase goes to noun phrase prepositional phrase rewrite rule before we invoke eventually the NP goes to det end rule that we have to use in order to actually get any words at the beginning of the sentence. And as you can see, there's an unbounded number of times that we could apply this rule. Now, one convenience is that you could think of a partial tree, and this will be useful in terms of thinking about the data structures which are going on, which are represented in our minds during real-time language processing. You can think of a partial tree as marginalizing over all completions over all of its completions. And so it has a corresponding marginal probability in the grammar. And this actually works great. So for example, here are 3 trees: the dog near the cat, and the dog near the dog, and the dog near the cat, and there are those tree probabilities. Those are complete trees. And I could, for example, say, hey, look, I'm going to actually underspecify what this thing rewrote as. I'm going to say I'm just going to represent it as this noun symbol, and then so the resulting probability will just be 12/81, which is the sum of these 2 complete tree probabilities. And I could have alternatively gotten that value by just multiplying through the rewrite probabilities of all the rules in this incomplete tree. I would have just not used any rule for the completion of this n right here, and then I would have gotten out a probability. And that actually will turn out to work. And I could do this even one more level. I could actually only rewrite to this level and underspecify all of the infinite number of possible completions of this prepositional phrase, and I would wind up with a probability 4/27, and so forth. But I'm still stuck with this infinite number of trees where there was nothing in here for me to sort of not specify, because I had to fully flesh out a connected path from the root of the tree all the way down to the first word. And so I had to keep on specifying things. I would ideally like to sort of underspecify the number of times I applied the NP goes to NP-PP rewrite rule, but this didn't give me an obvious way of doing that. However, you may notice that these tree probabilities form a geometric series. So we have 4/9, 4/27, 4/81, and 4/243, and so forth. And so actually, we can get the answer out by invoking the rule that gives us the that gives us the sum of a geometric series, and it turns out that this gives us exactly the right answer, 2/3. So this infinite set of trees, if you sum up this infinite series of incomplete trees, if you sum up their probabilities, it does give the right answer of 2/3. So, but how might this be implemented in a more generalizable way? Okay, so it turns out that there is a generalizing way of this geometric series trick, and this series trick is invoked by rule recursion. And the way of doing this for incremental left to right trees in a probabilistic grammar is as follows. And this is an algorithm due to Stolke in 1995, which has been very influential in computational psycholinguistics and also for any kind of models of left to right real-time language processing using linguistic structure. And this is what's known as, this section is going to be what's called the probabilistic Earley algorithm. So in general, these infinite tree sets during left to right processing arise due to left recursion in a probabilistic grammar. So for an example of left recursion, NP goes to NPPP was a simple recursion of the form A goes to A something, but you can also have more complex chains. For example, A goes to B something, and then B goes back to A something. And you can get this arbitrarily complex, but of course, there's only a finite set of non-terminal categories. So there's still a finite set of different chains from A through the leftmost daughter to back to A. And we can take advantage of this by forming what's called a stochastic left corner matrix of transitions between categories. And that's represented here as an example. So this would be the probability that, this would be the sum probability of all the rules that A rewrites to something that has A as its first child, for example. This would be maybe the sum probability of all of the rewrites that A has to rules that have B as the first child, and so forth. And then we can actually solve for the closure of this matrix. And then we can use the entries in this closure matrix as follows. So actually, it turns out in our model, for our little grammar, our end noun phrase grammar, the left corner matrix looks like we see here. Okay, and it has a lot of zero entries, which basically indicate that a category is unreachable through a series of leftmost children. And then there are some entries which are 1, and more interesting are the entries which are greater than 1, which turn out to be cases where there are ways of looping through sequences of rewrites and getting back to the same category. And in particular, these occur when the leftmost daughter we're talking about is the noun phrase daughter. And that's going to be important in getting the inference to work right. So we'll refer to an entry in this matrix as the R matrix of X. This is a left corner, transitive left corner rewrite, left daughter rewrite rule. We'll refer to that as Rx goes to Y. And this is sort of, you can think of that 3/2 as a bonus accrued for left recursion of noun phrases. And we actually, there's another matrix that we would use. It won't turn out to be relevant for this grammar, which is the unary closure matrix. And you need that because unaries also are sort of a kind of left corner, or a kind of leftmost daughter, and they need to be accounted for as well. And once we have this, we can set up the probabilistic Earley algorithm. And I'm slightly oversimplifying it, but this is pretty much what you got. And there are implementations around that you can use of this that just work out of the box. So you then, with these infinite tree sets, you designate 2 fundamental types of operations. One of them is a prediction operations. And the idea is that suppose you're midway through parsing and you've predicted that you have at some point you think a category of label Y is likely, it may come up next. And furthermore, Y can be rewritten to Z through a left corner, through a sequence of leftmost daughters. And then there's a rule that rewrites Z as some sequence alpha. Then we predict a rule Z goes to alpha and set up alpha as a new sequence of goals. So there's a notion of goals in the probabilistic Earley algorithm. Second, there's completion. If Y is a possible goal, then, and that is that you're looking for a Y next, and Y can lead to Z through unary rewrites, and we encounter a completed Z, then we absorb that Z and move on to the next subgoal in the sequence. And so we're going to represent a chart, the state of left to right processing as a chart of states, and it has the following structure. So there's every entry in the chart, every state entry in the chart has a goal symbol, and it has a set of sub-goals. And some of them have been completed. This is like I'm partway through a constituent. And the alpha part is the part that I've completed, and the beta part is I haven't completed yet. And we're going to keep track of two probabilities, one which we call the forward probability, and one of which we call the inside probability. The forward probability is the total probability of getting from the root at the start of the sentence through a sequence of parsing actions, that is, tree construction operations, through to the state that you're currently in. So it's the total probability of all the actions that would lead to the state in question. The inside probability is the bottom-up probability of the state. So it's the probability of whatever is underneath that state, word sequences, with the rules. And we'll see this in operation. So the two inference rules for probabilistic Earley, the prediction rule says, if I have something in a state which is of the form x goes to a completed set beta with the next incomplete state is y, so this is the next upcoming subgoal, and then other subgoals potentially. And I have in my R matrix, my closure matrix, this thing, then I can rewrite, and then furthermore, I have another rule in my grammar. This is a rule from the grammar that says with probability B, category Z rewrites as alpha, then I insert a state into my chart, which is predicted, and it has forward probability A from the closure matrix, B times from the grammar, and P from the forward probability. So you can think of this as you already were in a state with forward probability P. You then, the sum total of ways to get to this rule through a sequence of left corner rewrites, that's this value A, although A may be greater than 1, which reflects the multiplicity of possible probabilities. And then B is the probability of this rule operation. And so you multiply A times B times P. And that's the new forward probability of that state. And then B is the inside probability. There's no internal content to this rule, to this state, because it hasn't completed any of its subgoals. So its inside probability is simply the probability of the rule itself, B. And then the completion operation says if I'm looking for a subgoal Y, and I can, through the unary matrix, get from Y to Z, and I have a completed Z at the right place, then I can complete my subgoal Y, so this little dot which indicates which of the goals I've completed moves forward. I've now completed Y, and I multiply through the unary rewrite probability with the inside probability of the completed goal and I multiply the forward and inside probability of the X of this first state, and I get the new probabilities, forward and inside probabilities for the resulting state. Now that all sounds really abstract, but I'm going to show you an example of walking you through application to an incomplete sentence. So we have our grammar, that very simple grammar, and let's suppose that we're looking at the word sequence the dog near the. So the very first thing that happens is that I automatically get for free that I have the root category and I want to complete it. That's like an initialization. So I say that that's my starting point. And so with forward and inside probability 1, I start out the sentence with the noun phrase. But the noun phrase hasn't been completed at all. It actually has no internal content. But that's the goal. The goal is to complete a noun phrase. So this is a top-down model. And so the grammar is always guiding what you're looking for. Well, the prediction says, if I go back for a moment and I look at the prediction, I say that if I certainly can't complete anything because I have nothing completed, but I can predict. And I can predict that if the next thing I'm looking for is a noun phrase, then anything that I can get to from looking for a noun phrase, anything that a noun phrase can left corner rewrite to, I will now create new predictions, and I'll use the entries in the right corner in this R closure matrix. And it turns out that you may remember that there are two noun phrase rewrite rules. NP goes to NP PP, and NP goes to determiner noun. Both of those will be invoked. And furthermore, I can actually get to determiner through a left corner chain from noun phrase to determiner because of this rewrite rule. And so I'll also predict a determiner rule. And so what are the predictions that I've made? So all of them have no completed subgoals, and they have inside probabilities which correspond to the rule probabilities. You may remember that in the grammar, NP goes to det n has probability 2/3. NP goes to NP PP has probability 1/3. Det goes to the has probability 1. Now let's look at the forward probabilities. The forward probabilities come from the left corner matrix. The closure of the left corner matrix, and you get this. The entries here were 3 halves for this one and 3 halves for this one, because this is the NP category, and that takes into account the possible recursion through NP categories. And then the rule probabilities themselves are 2/3 and 1/3, and we started off with a forward probability of 1. So these entries are going to be the forward probabilities of these things. Okay. What can I do next? Well, I've done all the predictions I can do at this point, but now I can consider completion. In particular, here's a case, here's a state where I'm looking for the word the, and I actually have a complete word the down here. So I'm going to do completion here, and that's going to lead to a new set of states, both one that completes this rule, and then in turn, also one that fulfills the first goal of this rule. And I'll move the dot over here, and now I have determiner has completed the subgoal the, and now I have also a noun phrase that's completed its first subgoal of determiner. And now I can do prediction again, because I'm still looking for a goal, namely the noun goal. And so I do prediction based on noun, and I wind up with predicting noun goes to cat, noun goes to dog. Here, these had forward probability of 1, but you may remember I need to multiply through the inside probabilities, and that will give me these values here. And that, in turn, since I'm predicting dog at this point, I can combine this thing and dog to create a noun with a completed goal dog. That, in turn, allows me to complete this thing. This and this can combine, and I get a noun phrase that has completed the goal's determiner noun, but that also at the same time allows me to complete the goal's noun phrase goes to noun phrase prepositional phrase. I can complete that goal, and actually I can complete a sentence here. I can complete the root NP goal. And I could be done here, right? So this says that basically that it's possible for a sentence to end here, because I have completed the only goal of the root category, which is a noun phrase. And that sentence has inside probability 4/9. So the total probability of the dog as an entire sentence is 4/9. And that actually makes sense, and I encourage you to go back to look at the grammar and ask yourself, why would the probability of the dog as a sentence, as a complete noun phrase, the complete tree in this grammar be 4/9? And it should be. But of course, I still have this one state where I have not completed a subgoal, the prepositional phrase subgoal. So I can predict from my prepositional phrase subgoal. And I predict what I can predict from that. I can predict that a prepositional phrase rewrites as preposition noun phrase, and through the left corner relation, I can get from prepositional phrase to near, and so I'm predicting preposition goes to near. Okay, so that in turn allows me to complete, at this point, I'm going to complete this subgoal right here, and so now I have completed these things. Well, first I complete this subgoal, and then this subgoal. That in turn allows me to predict again from this point, and I predict the same way that I did here from noun phrase, and I'll do all the same predictions as I did up here. And so I get all of those same 3 predictions as I got in the upper left here, but they now have different forward probabilities because their forward probabilities have to be multiplied through, by the thing that I was predicting from, which is this. And now with the, I can actually do more completions here. And now at this point, if that's all the input that I have so far, I'm done. And this number, the forward probability of the only state that has just completed the last word in the most recent word, my input, that forward probability is the forward probability of the prefix. So if we have just processed word w sub I, then the prefix probability of w1 through I can be obtained by summing all of the forward probabilities of items that result in the chart that have the form something goes to a set of completed goals, followed by w sub I as a completed goal, followed by some possibly empty set of completed goals. And so that gives us the resulting prefix probabilities. And in our example, we saw, if you go back to the last slide and look, that the probability of one, the prefix probability of the is 1, of the dog is 2/3, as we reasoned before. As the dog near is 2/9, as the dog near the is also 2/9. And if we continued on, we would get different probabilities. We'd have to have dog or cat next, and the prefix probability would go down. And we could take the ratio of these prefix probabilities and get conditional word probabilities. So for example, the probability of near given the dog would be 2/9 divided by 2/3, or 1/3. And actually that will make sense because the probability of prepositional phrase goes to preposition noun phrase is 1/3. And so it reduces to the probability that a noun phrase would have a prepositional phrase modifier, which is exactly what should happen. Okay, so it's useful to think of probabilistic Earley as what's called an eager algorithm. So the inside probabilities of the states on the chart actually implicitly encode the distribution on incremental trees. You can, anything that will sort of give you that you can go from the root all the way down to all of the leaves and cover all the leaves will be a tree, and you'll multiply through the inside probabilities. And actually it'll turn out that this posterior distribution is precisely the correct result of the application of Bayes' rule. And so you can actually think of the probabilistic Earley algorithm as performing rational disambiguation. And the paper that brought this algorithm to attention in the psycholinguistics literature is Hale 2001, and Hale called this the eager property of an incremental parsing algorithm. So there are some incremental parsing algorithms, if you study more deeply in parsing, that don't have this property, and in fact they don't actually complete all of the structure. Not all the structures they construct are totally connected to the root of the tree. And or they will construct structures that are totally inconsistent with the tree and carry them too far forward. And this algorithm does not have that property. It completes exactly and only the structures that are possible given the input. And another thing to note is that we can think of these probabilistic grammars as actually doing both disambiguation and calculating predictive distributions over upcoming events. And this also turns out to be a polynomial time algorithm. So it's cubic in the length of the sentence in time and quadratic in the length of the sentence in space. And the prefix probability of the string is essentially a side effect of this incremental disambiguation. And so then we can connect this back to psycholinguistic theory, and what we'll do next is connect this to surprisal and see how we can use this to study incremental processing and differential difficulties that seem to arise from syntactic reasons. Now I want to point out that this actually is sort of psychologically implausible. Certainly if we as humans had cubic time language processing, then when a sentence doubled in length, we would take 8 times as long roughly to process it. And that's not what happens. We're close to linear time processors. But in spirit of rational analysis, we're going to start off with this model because this is a model that captures normative probabilistic inference under a probabilistic grammatical model. And we're going to make minimal computational assumptions. And that is that that assumption is effectively that native speakers deploy knowledge in a way that's effective enough that what we're doing is nearly indistinguishable from normative probabilistic parsing. And so that even though this might not be plausible in an actual computation time perspective, it might actually be a better approximation of human cognitive state and human performance than what might seem on the surface like a less cognitively plausible approach. So what we're going to do next, we're going to stop for a moment, and then we're going to turn to the application of probabilistic grammars in accounting for psycholinguistic data and real-time processing.